So I'm glad so many people want to learn about our experience with Cassandra. Our usual competitor is Microsoft, but today our competitor is Netflix, right? Big Cassandra user, and I'm glad that we're interested to other people to learn from us. So today we're going to talk about our experience with Cassandra. As some of us might know, we have a very small team. We spent probably 6 months before the launch. We were not sure if we're going to use Cassandra in production. In 6 months, after we made the decision, in 6 months we designed our horizontally scalable system. We deployed it to production, and we survived the launch. We kind of won console war. And also, it's in production. It's full speed in production right now. So, myself, I'm Alexander Filipchik. I go by Alex. So, I worked at Google for a little bit. I worked at Betfair. And when I joined Sony, well, it's really funny. When I joined Sony, I found that it's actually that our particular team, San Francisco team, it's a really startup-y environment, and I found that I actually have this startup-y attitude. So, and that's actually helped us a lot during the launch and preparation.
So I'm Dustin, also a staff engineer. As you can see, this is a ratchet with a staff. But so, get it, guys? Okay. So yeah, I'm an avid gamer. Working for Sony has been a dream come true for me. So making this work was very valuable for my career. So hopefully we can share some of those lessons with you. And who's here to hear us, or who's here for the free PS4? I'm just kind of curious. Okay. All right. Just only like one honest person. All right. Yeah. Okay. All right. So go over the agenda.
Okay. So today, people are talking about journey towards Cassandra. So we'll talk about it too. We'll talk about Cassandra-backed PS4 features. What particular features of PlayStation 4 infrastructure and actually Sony infrastructure use Cassandra behind the scene. I'll talk about OPSI stuff, and then we'll finish with our lessons learned, because we think we learned a lot of interesting lessons. We did so many things wrong, but it all turned out to be okay at the end. Fail fast and be successful at the end, right?
Okay, so I'm going to go over kind of the journey towards Cassandra. It was a tough decision. It was one of those things we had to really come together and agree on some of this technology. So we can't talk about a journey without actually talking about the challenges that our particular team had to deal with. So challenges. For one, like we said before, we're a small team. Sony's a big company, but little do people know there's a lot of teams that make it happen. They're all a little bit different. They all do things different ways. Our team in particular was pretty small, very much like a startup, which means that we didn't have some of the operational support, except this guy, and right. So that was one of the big challenges. Legacy support. We also had to support some of our previous year's released features and make sure that those are still performing to scale. Any prod issues, we'd have to kind of just juggle support of that and also creation of new features. Hardware deadline. This one's an interesting one. I don't know how many software companies get to deal with this, but we had a very hard deadline when it came to the hardware. Hardware was going to be released November 29th of 2013. There was no changing that. Firmware was going to be flashed onto the console. There's no turning back. We had to make sure all our APIs were built and up to scale. We had to meet that deadline. There was no saying we're going to push an alpha PS4 or something like that. We had to really deliver. And also, we had to scale at peak time. So the launch of the PS4 was interesting because it was released on Black Friday, which for our legacy systems and current systems, it would be like we knew a spike was coming. We knew we'd have to handle the traffic that was coming, and that was a really interesting challenge, the kind of looming figure as we were going closer to the date. So why Cassandra? Some of these sound very basic, but they really mattered a lot to us when designing this technology. For example, the strong community. Being a small team, we needed a technology that we can rely heavily on the community and their learnings so we don't make the same mistakes. We made new mistakes, but it's okay. Horizontally scalable architecture, duh, yeah, sure. You really want this, but we knew we were launching with 1 million consoles. We knew this would grow. We really want to have a database that would scale with our user base. Good performance, another no-brainer, but honestly, yes, we need to be able to serve our customers with low latency, high reliability, and just be able to provide a very responsive service for them. Cost-effective. Cassandra is great for running on commodity hardware. I guess maintenance costs are significantly less than if you're talking about like an Oracle or a MySQL or something. It's a little bit more cost-effective to maintain. And it was a brand new adventure for us. It was good to, as our kind of culture, just kind of delve into some of the new technologies and really make it work in a prod setting.
All right, so you're probably wondering what kind of features are powered by Cassandra. So what's interesting, when I joined, when a recruiter called me and asked me, do you want to join Sony? I'm like, well, why does hardware company, why do you call me, actually? I'm software engineer, I'm on a web part of this universe. And then turned out that Sony has a lot of services, actually. Whole SNI is about software, not about hardware. So this is a PlayStation 4, actually, real screenshot. What's new? One of the features that's powered by Cassandra. It's our small Facebook, which is quite very powerful. Not all the features are exposed as for now, but it works like, it actually works like a mixture of Facebook and Twitter. Video library, we do stream, and for example, Voodoo or Hulu, one of our competitors, and then if you were following announcements, we'll be rolling out Cloud TV soon. So will be interesting very soon, actually. So my library, games library, is powered by Cassandra. What's interesting about game library, it's kind of entitlement storage. It's personalized data, what user own. And then we built an interesting solution like custom-based search engine that allows us to run a very, very fast queries to pull user-related data, any data actually. PlayStation Now, which is cloud gaming. I don't know if you heard about it. You should, because it generates a lot of buzz. So we run games on our hardware and then we deliver it via streams to PlayStation 3, PlayStation 4, and beyond. Notifications are powered by Cassandra. Next, Live Area is powered by Cassandra. To Live Area it's a place where you can get some information about game, a particular game. What's your friend, to see what trophies your friends are getting, or what's just to see what's going on with the game. You can see like recent activities, related items, so add-ons. Everything is powered by Cassandra. Our store catalog, this is web catalog. It's powered by Cassandra too. And PlayStation catalog is the biggest actually. It's on a scale with it has same scale as Apple catalog or Microsoft Xbox Live catalog. A lot of products, every single game, and a lot of movies actually. Pre-order functionality powered by Cassandra. It helped us a lot during Destiny launch, another big title. I'll talk about it later. PlayStation Plus feature powered by Cassandra too. PlayStation Plus, it's kind of community. It's a feature that allows us to help gamers to get insights on new games, to get new games, free games, and also it's a requirement to play multiplayer on PlayStation 4. So if this thing goes down, everything goes down. Recommendations. They use Cassandra, I would say. Remote download list. So if you buy a game online using our web store, you can push it to one of your PlayStation 4s or PlayStation 3s. Depends. It's actually or PlayStation Vita. Cassandra 2. Share button. You want to share your experience, upload a movie or create a small movie and upload it, or a screenshot, Cassandra. Authentication. So Disney is giving a talk about OS 2.0. We implemented it too, actually. And many more features, like TVs, talking to a lot of hardware, talking to our services that actually use Cassandra behind the scene.
All right, so let's talk a little bit OPC stuff. So the infrastructure. So our Cassandra is hosted in both cloud and physical data centers. Fun fact. We're several hundred nodes and growing. And we basically got to the approach that we do a cluster per feature. I think when we started out, we did it based off read-write patterns and all that kind of trying to be really smart and try to figure out ways to do it. But then we went back to cluster by feature. It was the most robust way of doing it. vNodes and assigned tokens, I think Alex will talk a little bit more about that, but we do have a kind of a mix. Right now, certain clusters are vNodes, some other ones are assigned tokens. And we use SDNX client. We're not using any of the other drivers currently. Okay, so that's for PS4 cloud nodes. So this is not the complete Cassandra ecosystem, but this is the kind of the part that we're responsible for. Data throughput, we're talking about gigabytes per second. We transfer a lot of data in between clients and our Cassandra. Our read writes, over 200,000 a second. That's a lot. Data size, we have tens of terabytes. This is mainly user serving data. It's not like user event data, which is actually significantly larger than this, but this is live data that gets served to the customers. And as was previously announced, we hit the 10 million PS4 sold mark, and then also we have 80 million PS3 sold, and we have, I guess, around 250 million users. Clusters. So, like I said before, we did this based off read-write pattern initially. It didn't work out for us. We had some interesting downtime due to kind of putting a little bit too much in a particular cluster. So we moved away from that to kind of decouple all of our systems. I just said that. Okay, so our seeds are referenced by DS names. This allows us to kind of change seeds behind the scenes without having to change any configurations or applications or anything like that. It just kind of works. So this has actually been a great help for us by doing this. It lets us do maintenance in a lot easier way. Side-state compaction, that's what we use typically. And we do some manual compaction for some column families. I don't know if anybody's run into a situation where your SS tables keep on growing, and for some reason they're not shrinking. And yeah, sometimes the full compaction is the only thing to really get it out of there. So a typical node, as you can tell by saying this, it says we're in AWS. So we have N24XLs, and we're also using some I22XLs. About the same. One is a SSD-backed, which is really helping with some of our compaction problems. But that's kind of a typical kind of node in our world, which has two ephemeral disk. I'll probably talk about disk later, how we're configuring the disk, what we did during launch, and some of our lessons there. We put the commit log on the root partition, which helps when you need to restart a node or something. And right now we're doing everything via topology file. I know there's like EC2 snitches. At the time when we launched, we went with topology file, which we're managing with Chef currently. But it used to be a pain to maintain. And now it's a little bit more automated. But in retrospect, maybe we should have investigated a little bit different way of maintaining our clusters. Okay, so in AWS, the way we set up our replicas. So we just interleave between availability zones. So just having the adjacent tokens kind of be stitched between AZs. So obviously, if an AZ goes down, we still have some nodes going on. Right now, we're using, I believe, Chef to maintain all that right now. So when it builds it out. This layout, like I said before, we did some interesting things with this, trying different ways. That's one of the things we like to do is like try a lot of different techniques, even if maybe ill-advised. So we started out using a RAID 0 and get a higher throughput. However, with RAID 0, obviously if you lose one device, you lose the array. We had situations where this would happen, and that's why we were like, okay, well, maybe we should do a RAID 1. And you're probably asking, okay, well, you have replication factor. Why would you need to even do this? You have disk go out, you have a node go out. You're going to put more load on the adjacent nodes to transfer the data back, especially when you have a lot of data. So this reliability at one point seemed very important to us. But the problem with this, obviously, you get half the space, and also your throughput changes as well. So right now, what we're doing, we broke the RAID, we split it, and now we have configured Cassandra just to write to two partitions. So now we have some data in one partition and the one in another disk. So that's what we're doing right now. And we had to split the RAID because we're running out of space. So that's some interesting emergency maintenance there. Cluster resizing. Many of our assigned token type clusters, no magic here. We just double. That's it. Moving nodes, we could do it. It's a very network-heavy operation. What we found is network has always been kind of a big problem for us, which I can talk about in a coming slide. We had this kind of learning of Thrift payload size. So we did hit this limit, which with the current code that we have, how we're handling particular users, we had some really power users out there who would own, I don't know how many it was, maybe over 10,000 games. Crazy, but it's true. And we're having this user, this really important user, report that, hey, some things are not updating. I can't see certain kind of games in my library, and that's obviously a problem. Temporary fix right now is to increase those kind of thresholds to allow this user to be able to write his data into our store. Not ideal. We may have to look into changing code, but for now, this was the way we got around that. Bouncing nodes. We had a situation with vNodes where you would add a node, and all the nodes would have a different view of the cluster. You'd have half your nodes think the other half is dead, that other half think the other ones were dead. They didn't agree on anything. So what turns out is that our iteration, our version with vNodes was super chatty. So when they're trying to communicate, it took such a long time to figure out what nodes were up. They would actually be reported as down. So changing the vconfig threshold lets it so the nodes kind of give a little bit more leeway to say if a node is up or down. So it kind of helped with that situation. Inter data center latency. I'm not going to talk till it finishes. All right. So one of the things we've seen with having multiple data centers, especially with the volume of data that we're writing, is that data will take a long time to replicate. And not only that is that because we do use VPNs, is that those pipes can be filled up very quickly. Some of the ways we got around that was, for one, sharding that kind of data by only replicating regional type data into those data centers and then not replicating to other data centers. That helped save a lot of data transfer, and we also added another tunnel to let the data transfer across. But that was one of the problems with having like a VPN type thing. It's kind of dangerous. It's always going to be a potential bottleneck.
All right. So one of the important lessons we learned, you want to monitor everything. Every single possible metric you can collect, you go and collect it. It helps a lot because when things going wrong, things going wrong very fast. We saw a domino effect, right? According to today keynotes, it's not possible. It is possible. You can lose all your cluster, 100 nodes cluster in matter of 20 minutes, right? It's cascading very fast. Out of memory errors, for example, very dangerous ones. Corrupted SS tables, another interesting thing that was one of the reasons we switched from read-write patterns to feature by cluster. That's to make sure our features are independent and some small feature cannot kill bigger feature, right? So just to make sure we don't have this coupled system sitting in one database. Yeah, because interesting things happening. So we use Nedges, we're using Kibana Elasticsearch to search our logs, we're using Graphite for application metrics. We not only monitor Cassandra metrics, like internal Cassandra metrics, we also monitor what is the latency between our apps and Cassandra's. That's important for us because really, I'm not really interested in what's going on inside Cassandra, right? If it's giving me 2 milliseconds or 1 millisecond latency between my app and Cassandra, it's fine. If it's 8 milliseconds or if it spikes up to a second, that's not good. And then internally, everything could be looking very, very good. I mean, it could be one bad node, and then all our nodes are fine. But there's another thing about Cassandra. And then, I don't know if you saw it, Spotify presentation last year explained it very well. One bad node can actually because of one bad node, your application latency can spike, right? It's not like one node goes down and all writes and reads against this node spiking, or everything can bounce. And there's an explanation. Yeah, you can actually, it's kind of very simple explanation because of the internal implementation and queues and the way Cassandra redistributes reads and writes. We also use AWS CloudWatch, not for everything, just to check stuff sometimes. Yeah, app level monitoring, which is Graphite. Ops Center, we have it. Yeah, we use it sometimes. We more rely on our own stuff, right, on what we build. So Destiny, I don't know how many people heard about this game. Very, very big game. A lot of people were waiting for it. It was launched on Tuesday. So yeah. Oh, cool. So what's interesting about Destiny launch is that our RPS spiked 5 times actually from the average. So a lot of people were waiting for midnight, and we couldn't afford actually. We couldn't afford any downtime at all. Everything went smooth actually. So here's some stats. So this line, that's our RPS. So as you can see, it was around against one of our APIs, not against whole ecosystem, right? Just to give you some idea. So at this time, it's Monday midnight. It's usually 500 RPS. So traffic was higher actually, just even before the launch. And then right at midnight, you see this huge spike of RPS. It was a very big hit. And then on the bottom, this is logarithmic. You can see our Cassandra latencies, actually, for some of our APIs, like get index latency, get catalog latency. And so you might wonder, why do we see here 2 milliseconds, like 3 milliseconds? And red line is probably 25 milliseconds. The thing is, our production system do not operate with a small, we don't transfer tiny bits of data. Sometimes we transfer a lot of data. For example, one of those calls transfers on average 100 kilobytes from Cassandra or to Cassandra per call. That's why some of our latencies are higher, but it's still, compared to legacy system, latencies are very, very low. So, lessons learned section. It was a very interesting launch. It was very crazy launch. Microsoft was with Xbox system was very close. They had more people, probably maybe 10 times more people than we had. And then we didn't have any choice. Actually, our dates were not movable, and we just had to make it work, right? We couldn't afford any downtime. On a launch date, we knew that we were gonna sell 1 million consoles, and then following months another 1 to 2 million consoles. So we didn't have any migration from old system to new system. Everything was built brand new. So on this day of the launch, we just pulled the plug, saying, "Okay, guys, here's our APIs, our clusters up and running. Go use it." And it was a very big hit for APIs, for Cassandra's, actually for whole infrastructure. So some of the interesting lessons we learned about STNX client. Cross-DC latencies. So we made a mistake in the config file. It's a very small mistake, but it gave us a lot of headaches. So STNX configs were not configured to send requests to local data centers. So our apps were going into random data centers, right? For example, from US to Japan, latencies were terrible. That was fixed prior to launch. Another interesting problem, imbalanced node traffic. Have you ever seen it? Anyone? When you have like two very hot nodes and all of the nodes just doing nothing. So it was another interesting thing. So STNX by default uses MD5 hashing algorithm to find the node which owns a particular row key, right? So and our Cassandras were using Murmur3. So what was actually happening is that STNX was constantly sending traffic, picking wrong coordinator nodes. And because Murmur3 is 32 bytes and default hashing is 128, I believe, right? You can imagine that everything that was generated by STNX, all the hashes were off. So that's why we had two very hot nodes. DNS caching in the JVM, another interesting thing. So in EC2, different things can happen. For example, Amazon can send you a notification saying, you know what? Your node will be decommissioned. Your physical instance will be decommissioned in 2 weeks, or in 3 weeks, or it's actually, it can go down. Amazon had a pretty bad outage one day. So when they lost whole availability zone, and that's a reality. It's not it's not like it could happen. It happens all the time. So DNS caching helped us because we could DNS using DNS names for our seed nodes helped us because we had this ability to swap instances behind the thing. But if you're gonna follow same strategy, remember that JVM by default Java caches DNS names. So you can fix the property, you can change the property, but if you don't do it, it's not gonna work. Yep.
When you say seed nodes, are you talking about seeds in Cassandra.yaml, or are you talking about client seeds?
Client seeds. Yeah. So this is our tale of two nodes. As you can see, two nodes very hot, other nodes almost doing nothing. It's pretty good situation because what we saw sometimes is like 60 to 80%. CPU utilization, 3 times more traffic in and out. And other nodes 20. That's how it looks now. CPU utilization numbers are not correct. It's high, but we captured it when we fixed the issue. So, other interesting lessons. Single bed node can raise app latencies significantly. It can raise latencies. It It can, and it can be in, so your latency will spike and then it will go down, but it won't go down to the same level as before. And then such a situation, it requires fast actions, because it could be that node is cascading. When you see latency spike, you don't know what's going on with your cluster, actually, right? Without checking some stats, because it could be that one of the nodes just died, or it could be we had a situation when one of our nodes actually started to fail for no reason, right? The way we found it is that we saw that 3 other nodes actually gathering hints, gigabytes and gigabytes of hints. And they constantly, and they were failing to transfer those hints to one of our nodes. The strategy for such a situation, at least what we learned with our limited operational support, we just rebuild node. We don't bother with fixing it. Bad node, we just rebuild it in real time. It usually depends on instance size. It depends on data size. It takes from several minutes to several hours, but it's actually safe. You can do it. You won't see any downtime actually if you're careful, and then it's very fast. Yep. Taking out an entire Cassandra cluster is very, very easy. By very easy, I can give you some real examples. If you write a lot, you can fill up your mem tables very, very fast. Then out of memory can follow. Out of memory will cascade across whole cluster. We saw it. We didn't see it in production. We saw it during our stress testing across all our APIs. The fix was to scaling up, the first fix, and the second fix, we compress everything we write to Cassandra. We're trying to minimize traffic as much as possible, because it's easier to scale our app layer, right, by adding more Tomcats. We use Java. It's much easier, and then it's much easier to do a compression on an app side, on a client side, then write to Cassandra and wait till it compresses, and then has this risk to kill it. Another thing, SQL query. I'm not sure about latest Cassandra 2.1. On a version we run, you can kill Cassandra node by running a wrong query. You can do it, actually. If it's not indexed, you can especially be careful if you created your schemas using Thrift, using Cassandra client, and then you try to do a stupid thing like, oh, how many rows? Let me do a count. It can bring node down. You'll see out of memory. You could see out of memory exception. Corrupted SS tables. That's a funny one that we learned 2 weeks ago. So we have a big cluster that's powering library feature, user level data, tens of terabytes of data, and then same cluster hosting a small key space. Not probably very small, but not as big as first feature. And then we get this error in production, corrupted SS tables. One node starts throwing it, and it died with out of memory. Then second node, then third node. We lost 8 nodes in 8 minutes. That was very interesting experience. So the fix was just to sacrifice one feature. Yeah, just for some time, just stop it and then fix the problem. So that's our operational support, pointing on a huge spike.
That's a good picture.
Yeah, so that's a good example of one bad node actually raising app latencies. It spiked. We removed the node. Actually, another thing, right? If we see that we have a bad node, the first thing we do, we just remove it from a ring. We just stop Thrift protocol. We can afford hints. We can like find it will be gathering hints on other nodes, but we need to fix it as fast as possible.
Okay, so some of the things that we're end up monitoring a lot more after many of the issues that we had during launch is memtable flush frequency. Like you were saying, like we had a single node can cause significant latency across your entire app layer. During, I guess, Christmas time, we would just see this latency of some of our servers just creep up and then just like kind of do somewhat of a step up and then just continue to get worse. And it always would boil down to a single node that was flushing memtables a lot. And for a while we were just, okay, let's just deal with this and kind of restart it. and what's funny is like restarting that one node brought all the app latency back down until it happened again. So that kind of says that, that made us really monitor this kind of situation a lot, and especially during some of the holiday seasons. Hinted handoffs, that's pretty common practice. But I think when it comes to hinted handoff, what's up? Root cause of that one, man, what? It was traffic, and also we had the hot nodes. So when we had the two hot nodes thing because we were using token aware, so when we had token aware with the bad hashing, all traffic to one guy, he's coordinating everything, fixing that helped alleviate this particular problem as well. So it was kind of it's bad usage. But yeah, so hinted handoff, it's good to know that, we have hinted handoff. It's happening. It's, bad stuff will happen, but it's also good to know who they're failing to. Garbage collection, you always want to avoid those whole GCL situations. Compactions, Alex will talk a little bit more about compactions later, but yeah, that's seeing how frequently it's happening. If you're caught always compacting, and kind of the data sizes that you're dealing with there, you may need to kind of reevaluate, or maybe add more nodes or figure out why it's compacting so much. And histograms. So another Sony guy is has a presentation about histograms this afternoon. You should definitely check it out. He's gonna go in more detail, I believe. Okay, so what we found, VPNs are a dangerous bottleneck. More data transfer, the more your nodes get backed up. Easy to rebuild a node to fix, talked about that, and backup data. Replication factor helps, but it doesn't protect against data corruption. So, and denormalization cost. They always say denormalize, but it does come with a cost because this is cheap, but EC2s are not. TTL on almost everything. Keep disk size small. Yes.
So how many tables or column families do you guys have? You said denormalization costed you. It's all a few.
No, we have quite a bit of column families. I only know if I don't think I have enough fingers for that. So, and because we have a lot of TTL, sometimes you want to adjust your GC grace period if the data is not that important. If you have nodes down, you don't care about the zombie record coming back, adjust your GC grace period just to make sure that data gets removed eventually. Transactions, be creative. Use 2.1. It's supposed to solve it. Okay. All right, load test with real data. Okay. I need to wrap up pretty quick here, but replication strategy based off your, different usage patterns. You really want to tailor your replication strategy towards that. If the data is source of truth or not, it's really important. Make sure you have a really good replication strategy. Where the data is located, different data centers, have your local data there. User level versus app level data. Like app level data, more replicas, or else you create a lot of hotspots. Cluster-wide commands should be staggered. Global repairs are bad. If anybody remembers that. Yeah, so don't do it, especially if you do have a lot of automation. Be very wary that automation could also mean fat fingering something and pretty much screwing up your entire cluster. Okay, really quick.
Tokens. So we started with vnodes. We started because we thought, oh, from an operational perspective, it's really easy. We don't have a lot of DevOps, so we thought it's a good idea. But increased chattiness on Gossip protocol with vnodes, that was 1 year ago. This bug's supposed to be fixed, but we saw slowness in repair and cleanups. And also, Asterix client doesn't like vnodes because of the pooling mechanism. Also, one of our vnodes cluster crashed 1 week before the launch, and then actually we spent whole day trying to bring it up, and then in the next day we decided that no, it's too risky. We converted 70% of our cluster to assigned tokens. We used custom-built streaming library to stream data between vnodes cluster and non-vnodes cluster. It was done in 1 day, 4 days before official launch. Compactions, yeah, worst enemy, larger disk usage, high CPU, longer compactions, very painful, very, very painful. Sometimes we disable compactions and then run it when our traffic goes down. Level compaction with size tier, tried it on several nodes in production. Startup time, CPU trade-offs, iOS. Startup time is interesting. It's not really clear, but you know it will, because a lot of files are generated, you'll spend much more time rebuilding nodes. So if you stop it, it won't take 1 minute to start. Updates removals, it up disk. Some of our nodes had 200 of gigabytes of real data and 400 gigabytes of removed or update data, right? So that's it. That's our journey towards Cassandra. And this last slide, of course.
Okay, so I mean, we don't have a lot of time for Q&A, but we are going to be in the Cassandra Live section downstairs, and we'll be able to personally answer.